Okay, thank you for the kind introduction, and dear audience, I'm very honored to speak today and share my research in computer-assisted surgery for the operation room of the future. So let's start with an historical operation room. As you can see here, it was taken nearly 80 years ago, and you see it's clearly arranged and the infrastructure seems to be manageable. So in contrast, we have a scenario in the operation room in Heidelberg today. It's a highly complex environment. We have a lot of materials and instruments, different medical devices. We have assistance systems, for example, that provide navigation information. We even have robotic systems in the OR. And all these systems provide a huge amount of valuable data that can also lead to an information overflow. So the goal of computer-assisted surgery is to optimize patient therapy during surgery by turning the available data into useful information using methods from computer science. So what I mean with information is, for example, as you can see here on the right, visualizing structures like the vessel tree or tumors, which are underneath the organ surface, so not visible to the surgeon, and to help him to navigate to these structures. So you are all familiar with navigation systems in your car, and the concept we apply here during the operation. So what do we need for it? First, we need a map. And in this case, we have images from the patient. Then we construct a 3D model for planning. And then we use this model to match it with the intraoperative scene and provide the navigation information by using augmented reality. So I will briefly now introduce the single components, starting with our 3D model. That's the map we need for navigation. So this is based on CT images from the patient, and we need to do a so-called segmentation in the image to extract the important information from the background. This is called segmentation. It's done for every slice by the computer, and in the end, we can reconstruct a 3D model of the target organ, for example, in this case, the liver. So we have a 3D model. What can we do before the operation with it? For example, we can use it for operation planning. So we developed a framework which enables the surgeon to look at all the data available for the patient in an immersive virtual scene. So this is, for example, 3D information. This is the model, but also the radiological images. So you can see here the 3D model. And it's easy to use and really intuitive. It's touchless, and it can be used before the operation. And it allows the surgeon to capture, okay, this seems to have a delay, to capture all the information in a really intuitive way. And he gets an impression of the spatial structures, but not only of the 3D model, but also of all the other data. So if we have now our map, our planning data, how do we match it in the intraoperative scenario? So you can see here a scene from laparoscopic liver surgery. That means it's a minimally invasive intervention where the instruments and the endoscope are inserted through small incisions in the patient body. So you can see here the endoscope image, and this is where the surgeon focuses on during the operation. But we have also our plan and a lot of other data. So what we want is to show him the navigation information directly in the endoscopic view. And we need to do a so-called registration. What does it mean? We have our preoperative model from the CT images. We have our intraoperative scene captured by a stereo endoscope, and we need to match both of them. But here's the big challenge we face. We have so-called soft tissue deformations. That means that the liver is constantly moving due to breathing, heartbeat, and instrument manipulation. And we need to capture that deformation. We need to have a kind of elastic map. And we can realize that by using biomechanical models. So we try to capture the mechanical behavior of the organs to compute the volumetric displacement inside the organ. So we know where the tumor moves and the risk structures like the vessel tree. So you can see here a respiratory deformation patterns, and if we know what kind of force is applied to the liver surface, we can compute in real time this volumetric displacement and use it for navigation. But we also need an intraoperative model that captures this deformation during the operation. And here we have a sensor, a stereo endoscope. So you are all familiar with stereo vision from the human vision system, but the computer needs to calculate a 3D surface in real time, and we developed a new method for it that reconstructs the surface in real time. It's really important that we have real-time capable methods because we want to use it during the operation. So the computer has to solve several problems, starting with the so-called correspondence problem. So he needs to find the corresponding pixels from left and right image, and once he has it, he has to calculate the 3D position. So you can see here the result of the surface reconstruction. So next, we have our preoperative biomechanical model. We have our intraoperative surface from the stereo endoscope, but now we need to match them to get the navigation information directly to the patient. And therefore, we developed a novel method called physics-based shape matching, which assigns charges to the surface of the different models. And then the biomechanical model slides into the surface of the reconstructed organ, and this is also done in real time. So in the end, we want to provide assistance to the surgeon to help him for navigation and to optimize patient therapy. But we don't want to show him all the information all the time. We want to provide the right information at the right time. So this is called context awareness, context-aware visualization. And to show you the concept, we have here two different situations. Once a blunt instrument is used, once a sharp instrument, and we provide different assistance functions. For example, we show the tumor, the vessel tree in the resection line if he uses a sharp instrument, but we also show if he uses a blunt instrument, only the tumor. So to give you an outlook, we can also use robot assistance in the operation room. And here we developed a context-aware camera guidance. That means the endoscope is attached to a robot arm, and he shows, he anticipates the next step and shows a visualization what the surgeon wants to see. And the novelty here is that he has learned from looking at previous recorded surgeries, and then in the actual intervention, he analyzes the endoscopic images, knows what the next step will be, and visualizes then according to the surgeon needs. So the OR of the future will be a so-called sensor OR. We won't have single devices anymore, but sensors which are connected and provide digital information which we can use to analyze. So further research questions are, for example, how can we predict complications during surgery using all the data? Or how can we, how does the process influence the patient outcome? Or, for example, how can we compare similar patients taking all the information into account? So I'm convinced that the success rate of surgeries can be improved by using computer-assisted surgery. So thanks a lot for the attention, and also I want to thank my group in Karlsruhe as well as the University Hospital in Heidelberg and the German Cancer Research Center, my close cooperation partners, and as well as my funding agency. Thanks a lot.